Hello, my name is Matthew. Welcome to my talk. The title is Are WANs Ready for Optical Topology Programming? The motivation for this work is that the demands on networks and connectivity are continuing to grow. And therefore the network is required to be more agile and robust. And in response to this, researchers have introduced programmability at different layers of the networking stack. For instance, software-defined networking for traffic engineering with systems like B4 and SWAN, and software-defined load balancers such as ANATA and maglev, and software-defined switches like P4, programmable data plane, Sonic, Sonata, and even smart NICs. And so the final frontier of all of this is the programmable optical networks and their interactions with higher layers. So what is optical topology programming? We define it as the ability to quickly and flexibly reconfigure wavelengths on fiber paths in an optical network. And so we want to investigate this in terms of quickly and flexibility. So by quickly, we wonder how much time is it that is required to activate long haul wavelengths? And with regards to flexibility, what are the higher layer interfaces for tapping into this capability? And these are the two problems that we explore in depth with this work. And so one problem with optical layer topology programming is that there seems to be conflicting perspectives on this with regards to wide area networking. And so there's evidence to support that the optical layer is currently ready and capable, such as OWAN, published in SIGCOMM 2016, where they use reconfigurable links and demonstrate on a testbed optical network bulk transfers for wide area networks. And then work from Mara et al. Shows a cognitive methodology for optical amplifier gain adjustment and dynamic DWDM networks. However, there is also evidence against that optical topology programming for WANs, evidenced by publications from OptSys'21 and 20, ONET, and the optical packet chasm, which highlighted that research from both of these domains, optical networks and networked systems, can make unrealistic assumptions about the capabilities that are available from the other layers. And methods for WAN link reconfiguration that were proposed nearly a decade ago still have no publicly recorded implementations, such as the Coronet projects from 2012. So we try to resolve this conflict of perspectives with measurements in our lab test bed that's shown in this diagram below. And we investigate the feasibility for optical topology programming by measuring the time that's taken to stabilize an optical path. And we use equipment that's commonly provisioned in WAN networks today. So in this diagram, we see that we have 3 pairs of 100 gig transponders. We have band multiplexers and amplifiers, 7 amplifiers on the path. And we have simulated distance on fiber spans with some attenuators placed between these fiber paths and amplifiers. And we also have a 100-kilometer span of optical fiber between 2 of the amplifiers in the middle. So what we do is we want to measure the time that's taken to stabilize an optical path on this network. And so we do some baseline measurements with this equipment as it operates out of the box with the default parameters. And this graph on the left shows the power input or the power output from the transceiver at the start of the path and the Q factor for the signal that is captured at the far end of the path. And by looking at the time between the first change in power at the sender and the Q factor read at the receiver, we see that it takes about 265 seconds in this instance for the signal to be ready to transmit data. Before that, there's this evidence of this power negotiation happening between the transceiver and the inline devices, such as the amplifiers and band multiplexers, as evidenced by this jagged saw line in the orange marker. And so the key takeaway from here is that if we can remove this power negotiation step, we might be able to significantly reduce the provisioning time. And so we try to do this. And so by manually setting the launch power from the transceiver, we're able to reduce this provisioning time from 265 seconds all the way down to 13 seconds. And that's shown in this plot on the left. Now, we still see that there is some significant time where the two endpoints, the transmitter and the receiver, are not observing any change. And so in this time, we posit that there's some amplifier to amplifier power management negotiations taking place. And these amplifiers have no manual interface for setting the pump power level. So this is time that effectively we can't really intercede with and improve in our lab test bed. But it does show some evidence of how we could do better. So if we could intercede in these amplifiers control loops to set the power level manually, similar to how we did for the launch power of the transponder, perhaps we could cut this time further. And so we do have two methods for interacting with these amplifiers, although they don't let us change the gain and pump power level. They do let us read measurements from the amplifier about those two qualities. And so one interface is TL1 and one is SNMP. And so what we do here is to try to figure out how fast we could possibly reduce the time to provision a signal. And we compare the time that it takes to read the power level from each of the amplifiers on this path with both interfaces, TL1 and SNMP. And we compare this time with the time to activate the circuit in automatic and manual modes that we showed in the measurements in the slides earlier. And so by doing this, we can kind of build an amplifier table that shows the different power settings for the amplifiers on the path when we go to provision a new signal. So ideally, we would like to have a local controller that is set up near the optical path, and it can read all of the amplifiers' power settings and set gain levels at the different amplifiers. So we would provision a circuit, read what the amplifiers' values are that they eventually settle to, and put those in the amplifier table. And then a requesting agent would make some request to add or remove some signal. And if we need to add a signal, we could look up in the table and see what were the levels that were set earlier by the protocol on the wire and set those directly instead of having the amplifiers all redo the negotiation stages every time that the set of wavelengths changes. So we build this little amplifier table, but right now it can only read values and check whether or not they're valid on the path. And unfortunately, we can't set the gain specifically from the amplifier table yet. But we do compare the time to measure and populate the table with the automatic stabilization time and the manual stabilization time. And we see that long haul links reconfiguration with the settings today for automatic mode on the 7 amplifier path is roughly 20 to 210 seconds based on the configuration settings. So in automatic mode, about 210. And if we configure things so that the launch power is set manually, we can reduce that to on average about 20 seconds. But if we could programmably configure the amplifiers on the path with this amplifier lookup table, we could theoretically reduce this time to about half of a second to 3.4 seconds, somewhere in that range, where 3.4 seconds was the time measured with TL1, and about half of a second was the time measured with SNMP. So clearly, this is much, much faster than the 210 seconds that we had in automatic mode, and even a lot faster than in manual mode too. And so just out of curiosity, we wanted to see what we could do for longer paths. since we only have 7 amplifiers, how fast could reconfiguration be, for example, on continental or transoceanic paths? And so for one of these transatlantic paths, we can estimate that the length of a cable would be about 6,400 kilometers long and would have about 80 amplifiers. So we took these measurements from our lab with 7 amplifiers and tried to project the reconfiguration time for these longer paths. And we used 2 different models to fit the data: linear regression and square root regression. And based on these, the models suggest that we could reconfigure the 80 amplifier path in 2.5 to 8 seconds. But of course, there's a lot more constraints in these settings, and the operating margin of these devices under the ocean and across continental paths have a lot more constraints, like due to temperature differences and oceanic pressures and a lot of other settings like that. So these numbers are not completely accurate, we don't think, but it gives us an idea of what kind of possibilities that we could see if we wanted to pursue this further and try to get these reconfiguration times down. It gives us a good idea of what we could strive for. So discussion and work in progress. It's our position that empirical measurement efforts can inform critical gaps between optics and networking communities. And also, there's this implicit assumption in a lot of networking research about a stable physical layer. And this model is at odds with the dynamic physical layer model that would be there if we had these reconfigurable optical topologies. And so we showed evidence that these minute-long reconfiguration delays that we observe today, they're partially a relic of this outdated stable physical layer model, because networking vendors were not planning to have links change at quick timescales. So hence, having a few minutes to set up a circuit each time might not have been a terrible thing when these were created, decades ago. But now's the time to reconsider these physical layer assumptions that are implicit in network protocols and hardware, because there's definitely ripe ground for improving on this. And so it's also our position that bringing optical topology programming to the WAN, it calls for a collaborative effort. And so here we think that enterprise and transit providers' input is going to be absolutely essential. For instance, if we were to deploy some software hooks for controlling optical devices, that this kind of collaboration between enterprise and transit providers would be essential. And their implementations for some software hooks for these optical devices, they should preserve the privacy and the security restrictions that are inherent in backbone WAN networks. So that being said, that concludes my talk. I'm happy to take any questions from the audience at this time. And if you're watching this later, feel free to reach out to me by email. My email is there below all of the slides, mhall@cs.uoregon.edu. And so yeah, again, thank you for your time and looking forward to having any comments or questions.